is talk about forces. This is where we're going to jump in today. So, I'm going to give you 45 seconds to write down a definition for a force. What is a force? Give it a shot. You and your brain, your pencil, not your buddy's pencil. Your pencil, your brain. Go. Okay. Why don't you talk to your neighbors? Compare your answers. Have a conversation. Thinking, is that going to work for you?
Well, we all said the same thing. Same amount of smarts.
On the level of smarts, we're at the same place. Okay. All right. What did you say? I want to know. I want to be part of your group. Tell me, what did you say?
Be on our same level of smartness.
Same level of smartness. Same level of smartness group.
You said a push or a pull.
A push or a pull?
Or an expenditure.
Yeah, and that.
A push or a pull?
No.
How many other people said a push or a pull? A lot of other people. Okay, it's because it's a pretty decent definition. What else did you write down? Anything else besides just a push or a pull?
We had a
Go, Brian.
mass times acceleration.
Mass times acceleration. Okay, so here's the deal. And this is me being a little bit funny, but also me trying to kind of separate in our heads the concept from memorizing an equation. Does that make sense? So, absolutely, that pops into my head every time I say force as well. But I'm going to put this up in a little bubble up here, because we're going to get to it. So you're saying F equals mass times acceleration, yeah? I would agree with that almost wholeheartedly. There's one little thing that's missing. Does anybody know what that thing that's missing is in that statement? It's little. Like some subscripts.
Is it like the force of gravity or something like that?
It's like that, but not that.
Oh, well then I don't know.
It's three little letters that sit right here.
Net.
Net. Have you heard the word net before? Net. What does net mean?
Total.
Total, all of them added together, okay? So F net, oops, come back. Thank you. Does equal MA, but, so yes, now I agree, but the reason I'm putting it up in this little bubble is we're not going to play with this right now. This is what's going to happen after we do our test next time. So like next Friday, we'll talk about this kind of stuff more. Is that okay? Right now, I just want to know what a force is. It is a push or a pull. What else did you say? Brittany, I heard you say something else to your group. I was eavesdropping.
A force is a push or a pull which acts upon an object.
Acts upon an object. Is that what you were going to say too?
Yeah.
I was totally going to say that too. Dang it. Yeah. Oh man. Well, you guys are equal smart because you were going to say it too, right? Okay. So it acts.
Wait, so I'm on the same smart path.
So it acts on an object. And that's important because objects, that's really what we're talking about. Whenever we're talking about force, we're talking about objects. Not only does it act on an object, but the thing that acts is also
An object.
an object. So it's one, I'm going to say, one object acting on another object. Does that make sense? And the reason that I want to make sure that we have this statement in there is so that we remember that it's an interaction between two things. Okay? If I pull on the frog, or I push on the frog, so I'm applying a force to the frog. If I was going to label that force, it would be the force of curling on the frog. Does that make sense? Two objects are involved. Everybody's happy? Okay. Now, my next question is, if there's a force acting on an object, does it have to be accelerating?
Yeah. Yes, it does.
No.
Who says yes?
Wait.
Who says no? Okay. Peter, why do you say no?
Because there could be two opposite and equal forces.
I was gonna just say like the table, like right now, like the table on the frog. The frog's not moving, but the table is still putting a force on the frog, and then there's gravity pushing it down, but it's still not moving.
Right. So just because there's a force acting on something, and this is the other thing that I want to write down, not really a definition, so I wouldn't have expected you to have this written down in your definition, but it's something that I want you to, again, kind of big picture, I want you to know, and that is that just because actually a force is acting, just because a force is acting, that doesn't mean, this is really not very pretty language, but whatever. That doesn't mean the object is accelerating. All right, that's important. And the example that Amanda just said is the one that we're going to talk about right now. Is that okay? Yeah.
But if A is 0, then how is there any force in that equation?
Right. You're looking at this equation, right?
Yeah.
If A is 0, how is there any force? There are forces, but what does this say? This says F
Net.
net, and net means
Total.
total, so all of them added together. Does that make sense?
Yeah.
It was a really good question. That's like the heart of what I want to get to today, so thanks. That was awesome. Yes, so just because a force is acting, that doesn't mean something's accelerating. It's only if the net force is not 0. But we're not going to deal with any of those cases today. Nice. That's all right. That makes life easier, right? Everything's always 0. Sweet. We can go home. Except there's a lot to do still. All right. So when we're looking at these forces that are acting on these objects, it's really important to draw pictures. We love drawing pictures, and we're going to draw these very special kinds of pictures that we're going to call free body diagrams. So a free body diagram, excuse me, is a representation of an object and all of the forces that are acting on that object. Okay? So I want to look at the frog right now because that seems like an easy thing to do. Here's the frog, he's sitting on the table. That is my object. So I'm going to draw a picture of the frog. And generally you don't want to spend 35 minutes drawing a picture of the frog. This is not an artist's rendition, right? You just need something. So usually I'm just going to draw a box, or maybe a circle, or in this case a box with eyeballs because it seems right. And then we're going to write down all the forces that are acting on this object. So, the question to you is, what forces are acting on the frog right now?
This force
What
of
you got?
gravity.
The force of?
Gravity.
Okay, now I'm going to be picky, because that's my job, okay? I want all of the forces to be, I'm going to go back up here, one object acting on another object. So what object is it? I mean, is gravity an object?
Earth.
No, right? The Earth is an object. So that's what we're going to have. We're going to have the Earth. Now, which way does the Earth pull on the frog?
Down.
Down. So we're going to go ahead and label it. So here we go. We've got the force of the Earth on the frog. And I want you to write it out just like that. Okay? It's going to take a little bit extra graphite, but you can handle it.
For a fun frog.
The force of the Earth on the frog. Now, Donald, when you said that it was the force of gravity. That's kind of like our shorthand version of it. So I am going to put that in parentheses right next to that force, so I don't forget. If this was the only force acting on the frog, then
It would be accelerating.
It would be accelerating, but I told you that everything we do today is not going to be accelerating, right?
It's true.
And if you look at the frog, is he accelerating?
No.
In our frame of reference. No, he's not. So that means there must be
Another force.
another force. Anybody else want to tell me what another force might be? Go.
The natural force.
I don't make that noise because of you. I make it because of that word. I don't know where that word comes from because I've never seen a textbook that actually uses that word, and I've never used that like in this case. It's another word that starts with N, and it's a really nice word that actually tells you stuff. Natural, like I don't even know what that means. Like, ooh, it's a natural. Like, what is that? It's like free thinking forces. I don't know. No, it's a normal force, and normal is not. So it's not like natural seems all natural, and normal seems normal. Like normal means something in math and in physics. What does the word normal mean? Does anybody know?
The force of whatever the object is on, pushing it up.
So that's what the normal force is. I agree. So let's write that down. So that's the force of, in this case, what object is it sitting on? The table. So it's the force of the table on the frog. And I want you to write this out every time because you're going to notice as we write these free body diagrams, it's always going to be the force of some object on the frog. Force of some object on the frog. You see what I'm saying? This helps you to double check to make sure these are actually forces that should be acting on this object. Okay? Now, normal. Normal. That word means something. Normal. If you have a circle and you have a tangent line, we say that the tangent is normal to the radius. What does that mean?
Perpendicular.
It means that it's perpendicular. Normal means perpendicular. Okay? Normal means perpendicular. I'm actually going to write a little list down here of forces. Because we've got lots of forces that we're going to talk about today. These are just the first two. So I'm going to go ahead and put them on my list. So number 1 is going to be the force of gravity. So that's the force of the earth on blank. And FG. And then I'm going to leave a little space because we're going to talk about what that means in a second. And then number 2 is the force of, so it might be a table. If you look at me now and you're going to draw a free body diagram of me, you'd have the earth uncarbling and you'd also have the floor uncarbling, right? So it can be whatever surface you're sitting on or talking about, right? So it's the force of the surface on blank, and we put Fn, so this is gravity, and this is normal. And the reason that I'm kind of drawing that out is because I really want you to know that normal, which means what again?
Perpendicular.
Perpendicular. The normal force will always acts perpendicular to the surface. Always, always, always. And so if you remember, if you get in your brain that normal means perpendicular, you'll always know where to draw that normal force. Because it's always going to be what to the surface?
Perpendicular.
Always. Like, that's it. So, like, you don't even think. That's nice, right? We like to not have to think as much. So we're good there.
With the perpendicular to the surface, like, what's an example of perpendicular? Like, why perpendicular? I don't know.
So, like, if I put my book like this, and now I have a calculator on the book, right? Gravity's pulling straight down.
Yeah.
Where's the normal force going? Perpendicular to the surface. So it goes this way.
Okay.
Do you see what I'm saying?
There's like a triangle force.
Yeah, and we'll get there. That's what we're going to do for the rest of the day today. Yes! So, does that kind of make sense? And the more we do it, the more it'll make sense, I think.
Okay.
The thing to remember is that it's not always just going to be opposite of gravity. Sometimes, like in this case. Because in this case, you add them up and they have to equal what? 0. And there are only 2 of them, so they have to be. So are we okay there? Yeah, one other little piece of information. a couple of little pieces of information. The force of gravity, we can calculate the force of gravity. And oh, by the way, the force of gravity has another name that is often used.
Acceleration and gravity.
Those are very different. Acceleration and force are different things.
All right.
But there's one word that also means the force of gravity. We talked about it on, I think, question 1 of the blue sheet. Starting with W, it's what? Weight, yes. So if something says that it has a weight of blah, 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 you know that that's what this is. Weight is just another description for force of gravity. Everybody's okay with this so far? Okay. Now, Addison, you said, when I asked about the force of gravity and the other thing, you said acceleration due to gravity. They're related.
But they're not, yeah.
But they're not the same, but we're going to figure out how they're related right now. Here we go. So FG, if you wanted to calculate it, like in the next problem that we're going to do, anybody remember how to calculate the force of gravity? It's really pretty easy. 9.81, which is the acceleration due to gravity, right? Times the mass, yeah. It's going to be m, so the mass of the object times the acceleration due to gravity. So mass is measured in kilograms. Okay. Are we all okay with that? The chemists use grams. The physicists use kilograms. It's that wonderful, confusing little thing, but we're always going to use kilograms, so just get that in your brain and then you'll be a happy kid. Okay? G is the acceleration due to gravity. We're going to measure this later in a couple weeks, okay? But until then, we're going to go ahead and go with it and say, okay, it is a constant, more or less, at the surface of the Earth, more or less, and it has a value of 9.81 meters per second squared downwards, right? So I'm going to go ahead and put that negative sign there. What are these little arrows that I'm writing above these things here?
Is it the vectors?
Yeah, we talked a little bit about vectors last time, right? A vector is something that has both magnitude and direction. So this is saying, okay, mass, that's just a scalar, that's just a quantity. You either have it or you don't. Okay, it doesn't make sense to say negative mass like that. What is that? That's nothing. Okay, but you can't have negative acceleration, something that's going down. So the force of gravity is also going down because it's negative something times a positive something gives you negatives. Yes, we okay there? Okay. All right. Issues, questions, concerns? No. Okay. Now I have a question for you, and I don't have the demo here because we're having this. Everybody needs the bowling ball. Do you have that problem in your house? Like you have one bowling ball and everybody needs it?
Yeah.
All the time, right? It's like, come on. Some people are fighting for the bathroom, some people are fighting for the bowling ball, right? So Mrs. Cross and I are fighting over the bowling ball. It's my bowling ball, but I let her borrow it. I'm kidding. Nah. Anyway, so I don't have the bowling ball, but I want you to imagine I have a bowling ball, okay? In fact, I have a little tiny bowling ball here that you can take a look at. Oh, it's so little. It's like bowling ball for, I don't know what. Yeah, maybe like I'm thinking like Beatrix Potter, like little, I don't know. Anyway, so bowling ball, little tiny bowling ball. If I leave the bowling ball here, assuming that the table is flat, which it's not, but let's pretend it is, okay? If it's flat, and so it's not going to roll anywhere, how is the free body diagram of the bowling ball going to compare to the free body diagram from the frog? Same, right? Now, as I push on it, it's going to accelerate. Do we agree with that? Okay. Is that what we're talking about today?
No.
No, we don't care about that one. But after I let go of it, so it was sitting still, I gave it a push, I let go of it, what's going to happen to that bowling ball?
It's going to keep going.
It's going to keep rolling, rolling, rolling. The beauty of bowling balls is that they're all shined up so we get rid of friction, right? So if I just push this thing and I let it go, and it's just going to roll, 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 roll. Yes, do you agree? Yeah. Until it hits something. Okay. During that roll, 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 roll time, is it accelerating?
No.
No friction, because there's no roll, 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 roll until it hits something.
Is it going down?
There's no applied force to it.
There's no other forces acting. So here's my question for you. How does the free body diagram of the rolling bowling ball, that's kind of a fun thing to say, the rolling bowling ball, how does that compare to the free body diagram of the frog?
It's going to be the same thing.
It's the same.
Because
why?
Because there's no active force on it. You're
nothing acting on it currently.
Right. Is this making sense? It's going. It's going. It's going. It's going to keep going, but it's not changing velocity because there's no extra force acting. Does that make sense? So I'm going to put this in big. We got to remember this. So this kind of a thing, this whole F net equals 0 business is true if the object is not moving and it's also, and this is the piece that I really want you to remember, because this is something that's like one of those kind of weird situations. The same free body diagram, except it would probably be a circle, because that would make sense. It would be a circle, but besides that, it would be exactly the same, even though it is moving. So this is true if the object is moving with what? With what again?
Constant velocity.
Constant velocity. Does that make sense to everybody? Is that okay? As long as there's no extra force acting, it's gonna go, it's gonna go, it's gonna look just like that. Everybody happy?
Yeah.
Okay. Yeah? Let's do problem. So you don't have a calculator. Well, I guess probably for the part A you won't need one, but eventually in the next, I don't know, 5 minutes you will. So if you don't have one out, you might want to pull one out now. If you don't have a calculator, you may borrow one of mine. On the wooden table, there's a little box that has some calculators. Just make sure that I get them back at the end of the block, please. But other than that, you are very welcome to them.
So according to that like free body diagram, that frog could be moving.
Yeah, you have no idea.
Yeah.
Isn't that kind of disturbing in a little bit of a way? Yeah, it's kind of strange. The only thing you know is that it's not what? Accelerating. It's not accelerating.
Yeah.
That's all you know. Don't know very much.
And that's because the forces, there's a continuous force of gravity and a continuous force of the table up.
Right. Exactly. Exactly. Okay. So this little set of problems that I have to do today, the whole premise is that you just got a gift. It's a box. It's a 10-kilogram box. You don't know what's in it, so you can put whatever you want in this box. Isn't that
It's
exciting?
a gift was the box.
It's just a box.
It says a mystery box. So it can have whatever you want in it. So I don't know, Brittany, what are you going to put in your mystery box? Books. Okay. Okay. Jack, what are you going to put in your mystery box? What'd you say?
Sleep.
Is that an object that you can you do that? You are that cool?
Yeah.
Wow. Is it is it a dense object or not a dense object? I'm gonna let you work on that. You can tell me. So what are you gonna put in your box?
10 kilograms.
Pick something. It could be puppies. It could be chocolate. It could be I don't know.
My little brother.
Your little brother?
Sure.
You want King's little brother? He's a pretty cute kid. Yeah. Okay. King's like kind of get rid of him. All right. So here's the situation. Zoe, your friend Keegan has given you a special gift. A massive 10 kilograms with a mystery surprise inside. Let me out! Let me out! The box is resting on a smooth, frictionless horizontal surface. Part A says determine the weight, but we know right away, before we even do anything, that means what?
Force of gravity.
The force of gravity. So that's easy, right? We can do that. And the normal force exerted on it by the table. Okay, can we handle that?
Yeah.
Let's do it. The very first thing you're going to do, because you're probably like, oh, I got that already. I can multiply in my head. I want you to get in the habit, because the next problems are going to be harder, of doing this right. So let's go ahead and draw a free body diagram, shall we? Draw a free body diagram of the mystery box. And once you've got your awesome free body diagram, then show it to your neighbor and see if theirs matches yours. feels a little redundant, maybe? Yeah? Lindy, what's one of the forces that you have written down?
Force of Earth.
Force of the Earth on the box. Which way does that one go? Straight down. Do we agree with that? Is that okay? And we're going to mark that, besides force of the Earth on the box, we're going to write what?
Force of gravity.
FG, yeah. Alright, other forces that you have? Casey, what else do you have?
Force of the table.
Fantastic. That one goes which way? Up. F sub n, yes? Alright, anybody else have any other forces yet?
No.
Good answer. Okay, so if we were going to figure this out, can we find the force of gravity?
Yeah.
Yeah, because we know that fancy little equation, right? It's just the mass times the acceleration due to gravity. And so that's going to be 10 times negative 9.81 meters per second squared. What is that? Without your calculator, you can probably figure that out, right?
Negative 98%.
Yeah, right? Does your book, do you remember, or have you guys seen, does it use 98, like 9.8 or 9.81?
9.81.
Yeah.
Okay. We'll go with it. Is everybody cool with that? Now, logically, just thinking about this, if FG is negative 98.1 newtons, what does FN have to be?
98.1.
Okay, so that makes pretty good sense, but I'm not going to make it that easy because it's going to get harder in a second. So I'm going to say F net equals FG plus FN, and those have to add up to what?
0.
0, because why?
Because it's not accelerating.
Not accelerating, not going anywhere, so it's got to be 0. Now I can say, well, these guys have to be the same. Opposite directions, though. Okay? So from that, then I can say that Fn equals negative Fg. So Fn is 98.1 newtons. Is that okay?
Yeah.
Alright, good. So now, here's the thing. Is it the normal force? It doesn't have an equation that goes with it, right? I didn't tell you an equation for it. And the reason is because it changes depending on the situation. So I want to tell you this little tiny story that it was like one of those weird, like, oh my gosh, physics is everywhere kind of experiences that I had this summer. If you haven't started having them, you probably will start this year because you'll be like, whoa, oh my gosh, what is, and it's a wonderful experience. So I was cleaning out the dishwasher, like not cleaning out, but like emptying the dishwasher.
All great stories start.
With
dishwasher.
right, with my husband, and this is how it worked. Right, so I was like holding plates, and he was just putting plates onto my hands. Can you imagine this experience? Right? Okay. Yeah. So there was a plate on my hands, and now if I drew the free body diagram of the plate on my hands, because this is what went through my head, I was like, whoa, this is crazy. What forces are acting on the plate?
We definitely know you're a physics teacher.
Yeah.
You're totally going to be doing this too. Just watch.
Force of carbon,
Just wait. Force of carbon and force of the
Earth.
Earth, right? Everybody's agreeing? Okay. And the force of carbon, how does it compare to the force of the Earth?
Same.
Same, right? Now, he's going to start putting more plates on top. If my force of carbon stays the same, what's going to happen to those plates? Right? Accelerate downwards, break, mess. Okay? But, what happens as those plates keep getting stacked on and on and on? Force of carbon increases. Do you know what I'm saying? Can you kind of imagine this? Or if somebody's putting like books in your arms or whatever, like you keep pushing up harder and harder and harder. So you're increasing your force in order for that pile of whatever it is not to fall. The normal force is pretty much the same way. It's not a cognitive thing. But I don't feel like when plates are being added to my hand that I'm like, okay, calculating how much force do I need to apply? Like that doesn't happen. Right? Your arms just do that. You know what I mean? And that's kind of what like the surface of the table does. So if I have the frog here and then I put, I don't know, a calculator on top of the frog, why, I'm not sure, but let's pretend, okay? What's happening to the normal force, the force of the table?
It's going up.
It's going up, right? Same deal, okay? So the normal force is dependent on the rest of the situation, which is why we have to write this down. Because for whatever reason, in part B, now your friend pushes down on the box with a force of 40 newtons. You're not trying to hurt your little brother, are you? Here's this box. I'm going to push down on the box now. So now Keegan is pushing down with 40 newtons. And the question says, again, determine the normal force exerted on the box. Is it going to be the same?
No.
Is it going to be bigger or smaller?
Bigger.
Big.
I wouldn't
Bigger.
the same. No, it would all be bigger. but
Yeah,
it's
it'll be
the
bigger.
scale.
Okay, so now I want you to figure out how we're going to figure that out. What has to be added to our free body diagram now?
The force.
The force of Keegan, right? So I'm going to say the force of Keegan on the box. And even though he's pushing from up here, I'm going to draw my arrow here so that it's like everything's coming from the box. Does that make sense? Just so I don't get confused about where things are going. Okay? And I'm going to call that force, it's not really a gravitational force. And it's not really a normal force. I'm going to call it an applied force, F sub A. Okay? And then in order to figure out my new normal, I need to add 1, 2, 3, all three of those forces together. Okay? So here we go. We're going to say that F net is equal to, oh, what are you doing? Sorry, there we go. Crazy thing. It's coming. It's coming. Is it back yet? Hey! And that has to add up to 0? Do you agree with that still?
Yeah.
Because it's still not going anywhere. It's still not accelerating. And now you can figure out that normal force. Okay. So Fn is equal to negative Fg plus negative Fa. So Fn is how big? Whoa, he was pushing with 40 newtons of force. I believe, wasn't it? Yeah, 40 newtons. So what's the normal force now?
138.1.
Do you guys agree?
I agree.
138.1? 138.1 what? Newtons. Okay. Now I want you to take a look at part C. I would like for you to do part C. I want you to draw a separate free body diagram, okay? If you would like, I can get you whiteboards. If you would like to do it on whiteboards, that's fine. Otherwise, do it just on your paper. So now the situation is that your friend is going to pull up. That's why I put a little bow on the top of the box. So your friend's going to pull up on the box, and we want to know the normal force now.
I thought it was a tree growing out of the box.
Yeah, I noticed that
No,
too.
it's a bow. It's like a pretty nice bow, right?
I thought it was his hands at first. Yeah.
Yeah,
So if you would like to work on the whiteboard together, you're welcome to. Was there a whiteboard back there for you
Or you could just pull him up by his hand.
You guys have a whiteboard right there. All right, so go, go, go. This should be fast.
Alright, I'll go back.
This one.
No, so instead of.
This one.
Yeah, because otherwise it would be very exciting, right? Yeah.
Yes, we do.
I just have looked at it.
Are we doing a 5-person?
We're a 5-person.
Yeah, you guys are a 5-person team.
Make this happen.
Do you want another one? I can get you another one. Will
That would be awesome.
He's gonna go.
It's kind of like its neck though, like his shoulder blade. Anyway.
He's a mouse.
Every single one.
Alright, so there's force gravity.
That's fine.
An hour last night, your driver's like, asking me about home. You gotta get one.
Alright, what was the force? Up.
40 newtons. Again and still. Yeah.
40 newtons. Alright.
How are we doing, team?
Force is applied.
Is it going to be bigger or smaller this time, that normal force?
Smaller.
Smaller, right? Smaller than even the beginning. Because if it was bigger, it would like, whoom, it would make it fly upwards, which doesn't happen. It's good to know that. That's not going to happen. Yes, it is still 40.
Plus.
If 10 kilograms is the mass of it.
So it'd be 9, oh boy, correct.
All right, are we ready?
Almost.
Not yet. Equals negative at the end.
Yeah, but what's that? Yeah, you could just subtract 40 or 98. You're like 58. Alright, cool.
What do we get?
Negative 58.
So Fn equals 58. No, but it's not negative.
Is that wrong?
Life is good?
It's not like this.
Life is great.
All right. So now, Jenny wants to know what's in the box too. So Jenny says, hey, wait. I want to see the box too. What's inside the box? And so Zoe's like, sure. Pull it over to yourself. So she's going to apply a little force along a string. But here's the difference. I have to add a couple of things to our story first. We need to add a couple forces to our story here. Number 3, the third force is one that we just talked about. We didn't actually write down, but I want to write here. And that's the force of like a person or something like that on the object. It's an applied force. That is not one that you would have an equation to calculate either. That one will either be given to you, Jenny pulls on the box with such and such a force, or blah, 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 here's all this information. How hard did Jenny pull on the box? That would be kind of the way that question would happen. There's another force, because unlike in the first part of the question, we're going to put this object now, instead of on a nice smooth surface, onto a rough surface. Okay? So a surface where there is some sort of relationship, and we have this thing that's going to slow it down. It's called what again?
Friction.
Friction. Now, we're going to think about this in terms of one object acting on another, because, right, that's what a force is. It's one object acting on another object. What object is it that's acting on my frog if there's friction involved? It's the table, right? So you've got the surface of the frog and you've got the surface of the table, and it's the interaction between those two that is this friction, okay? So when we label it up here like this, we're going to say again the force of the surface on the object. You see that this one and this one are the same, except they're not. But they're labeled the same way, okay? In parentheses, we're going to put FF. This is friction. And we're going to get more deep into friction in a moment, but for right now, 2 things you need to know. Unlike the normal force, which always acts perpendicular to the surface, friction is always going to act parallel to the surface. Okay? So that's the difference here, or a difference. So that's one thing that's really important to know about it. Another thing that's really important to know about it is that it will always oppose motion. it's never going to cause something to speed up. It wouldn't really make sense. In what we know of friction, right, in our like concept of friction, it wouldn't make sense for friction to speed something up. It will always slow it down. It will always oppose that motion. What's that?
It'd be funny to watch, though.
I know, right? It would be like a whole different like realm of physics rules. Not the ones for this universe, right? Like it doesn't make sense. Okay, so everybody's good with this so far? Now back to Jenny's story. I want you, well here, let's look at this together for a moment. So Zoe says, sure, pull the box over to you. And so then Jenny takes the box, pulled by the attached cord, because there's also a cord on, or maybe like a long ribbon or something. She's going to pull on the box with 40 Newton force. We got that. Here's the key. At an angle of 30 degrees.
Oh man.
Okay? The question says, calculate the friction acting on the box and the magnitude of the normal force acting on the box. It can be done? Yeah. The first thing you need to do is to draw a free body diagram. I would encourage you to do this one in your notes. If you understand this and just want to write it on the whiteboard, that's fine. But I want you to draw that free body diagram. I want you to talk to your neighbors. I'll draw it in a minute, but I want you to give it a shot first.
All right.
And certainly, feel free to talk to each other about it as we're going here.
Do we have anything to wipe this out?
I'll get you something. Hold on just a second.
Oh, it's back.
Yeah, pulling it up, so 30 degrees relative to the horizontal, upwards.
Oh, it's not on the side.
Yep, it's on the horizontal surface.
The smooth surface of the table.
Yeah, it's not smooth, I lied.
Oh, okay.
I actually edited the question, but I forgot to catch that.
So there is friction.
There is friction, because otherwise there'd be acceleration, and we don't want that. It's really okay to talk to each other, you guys. I promise. I won't yell at you. Are we okay with these two for sure? Okay, so now the force applied is going to be somewhere, it's above horizontal, so there's horizontal. It's going to go up at an angle of 30 like this. Okay, so if you're having a hard time picturing that before, that's what it's going to look like.
Could that force...
Oh my goodness, go away. Here we go.
Could that force, like, could the cord be attached to the bottom and it could...
Sure.
So...
Bottom, middle, top, it doesn't really matter. All that I care about, because honestly, when we're talking about this thing, we're really talking about it as a point place at the center of mass of the object, right? Because we're not going to cause it to like rotate yet.
Yeah.
That's like next semester. So I'm just going to put it from here. You could put it up here. You could put it like wherever you want.
Okay.
But I just like it to leave the box. Does that answer your question?
Yeah.
So here's my angle of 30. So this is the force of the friend on the box. That's an applied force. Oops. And then we said that there also was friction, right? Where's the friction going to be?
Parallel.
Parallel to the x-axis, going this way or this way?
That way.
That way, right? Right or left?
Can see.
It'd be to the left.
To the left. Yes. So it's going to say the force of the surface on the box, FF. So the one thing that's kind of different and weird about this is what?
That's not necessarily equal to 0.
Oh, it is equal to 0. I'm telling you it's equal to 0. It's equal to 0.
So the
Okay.
box doesn't go.
The box is going somewhere.
Yeah, angles in there. You gotta figure out what to do with them.
Yeah, there's angles in there. That's the weird thing. So this thing is moving at a constant speed. Everybody cool with that? If it's moving at a constant speed or a constant velocity, what do you know about the F net?
Zero.
0. 0. Always. As long as it's not accelerating.
Okay.
Right? Difference there. And that's the key. That again, we're trying to put that together
She
today.
only pulled with 40 newtons once and it just continued.
Nope. She's pulling with a constant force of 40 newtons. Constant force of 40 newtons, but there is what going the other way?
Friction.
Right, that's the key. Do you see what I'm saying?
Okay.
That's the difference. So she got it moving, so there was some acceleration that happened, but we don't care about that part. All we care about is, she's like, I'm taking this box with me, right? Like, goes like, wait, come back with my box. Okay, she's just walking, pulling this box with a force up like this, okay? It's moving at a constant velocity because you got friction going this way and the supply force going this way. Okay. The other weird thing, because if she was pulling straight this way with 40 newtons, this would be an easy problem, wouldn't it? Because we know that the force of friction must be
Equal to the force applied.
yeah, so like 40 newtons, right?
Yeah.
But
Angle.
it's not angles. Yay, Trig!
Gross.
Who said gross? Oh, yay is what you meant to say. All right. Y'all know how to do this, don't ya?
Okay.
Let's break it. Let's go. Here we go. Horizontal piece. So I'm going to call that FA sub X. Sorry about that. There we go. And then we're going to have FA sub Y. I'm going to let you and your partners work on this for a few minutes. Do you all know how to find FA sub X? Go Trig? Yes? If you don't, talk to your neighbors. If you all need help, talk to me. FA sub Y, same game. This plus this have to equal what?
Zero.
This plus this have to equal what? This plus this have to equal what?
Zero.
Go. Do it. Do it, do it, do it.
Okay, so there's 30 here, 60 up here. Yeah, so they just use that. The length, that's 40 newtons. That is 40 newtons. What's the counting rate? 30 to 90. Yeah, like a one more.
It's not an equation. You just, wow, everything.
Can you use, do you sine or sine tangent, right?
Oh, yeah, you can.
That's what you use.
Or you could just use, well, the easiest is if we do use
No, I do.
what is it?
For what? So you want to know what?
60, 90, you know what side is for closing it.
What kind of 30 square root of 3 over 2?
What?
What's kind of 30 degrees is square root of 3 over 2?
So what?
You just do cosine of 30
Just go in there anyway.
times 40.
Good. Libby.
30.
I'm gonna say
Yes, I don't know.
Wait, Addison,
What?
What against the,
Yeah.
adjacent over.
Alright guys, define, listen, define the y value, you just do 40 times sine of 30.
So we got-
Define the x value, you just do 40 times cosine of 30.
okay, so we do cosine.
30 times.
Sine of 30 degrees equals 1/2, and sine of 30 degrees equals 3 over 2.
If you are using sine and cosine, make sure that your calculator is in what mode?
Degrees.
Degree mode. If you are in a fancy pants math class and you're using radians, make sure you either switch it back or borrow one of my calculators. Those are both good options, but don't use radians. You'll be an unhappy child. How's it going?
Good.
Thank you.
3 degrees, right?
How are you?
Wait, so it's, I have a teacher yet.
Oh, we get like a regular.
AP1 over 40, you're doing cosine of 30, right? And, okay, so you're cosine.
So now that we have
So then, AP1 cosine 30 times 40. What is the cosine?
So you're done, John's done.
you can just type yeah, just one and
I want it in decimal form. Yep.
Cosine 30
It kind of mixed, but
times 40.
Just a friendly reminder, I'm hearing lots of good stuff happening. This is after you've figured out what these values are, this is your next step. You need to write these FNet equations down. That's really, really important. Getting these FNet equations written down, because that's how you're going to figure out FN, right? That's how you're going to figure out FF. This is what shows that you understand physics. Like, this is the key right here, that purple and orange. That tells you, or that tells me, that you understand what you're doing, and not just writing down random things and subtracting and adding them and crossing your fingers, which would not be good physics.
Okay, so 40 is the applied force, correct?
This one here, yes. Is that what you're asking?
Yeah.
How's it going? Are we doing okay? Is anybody stuck or need help or anything that I can do for you? Yeah,
Can you come explain?
of course.
Oh, yeah. Wait,
Yes.
okay.
Awesome. Okay.
Would you then?
This is where you got stuck? Okay. So all I want to do, one of the things, part B, I want to know FN. So I need to look at everything that's acting in this direction. And that's the y direction. So I'm going to say FN, I'm just going to kind of look at all the things that have arrows going up or down. This one, and this one, and this one. So that's where these come from.
Yeah, that would work as well. But
And it's not accelerating in this direction, so that means it has to move. Is that okay?
But if,
Yes.
The 40 is given to you.
So, no, so the diagonal one has been taken into account by
but
this.
shouldn't it work?
So these two add up.
What? For what? The y direction? Yep, and then 31.
Yes, exactly.
Gravity's not like me. Not even saying anything. So what'd you get for FA?
Yep, FA and A.
Yeah.
34.6.
So first we found out that.
yeah, I got negative 1.5.
Normal.
And then you're gonna put, so do you know how to find those two?
Yeah,
Yes.
it's 40, right?
Exactly. Yep, yep. Does that kind of get your ego
Cosine
going?
of 30.
Yes. Okay, thank you. You're welcome.
What do you cosine of 30, right?
Yes. This is.
Oh, okay, that's how you found it. I just picked the majority. Okay.
Oops, that's not what I wanted to write.
Find
So then just do something.
34.641.
Are you ready or do you need another minute or so?
Right.
Ready-ish? Somebody want to give me a value for FF?
Negative 34.6 newtons.
Negative 34.6. Do you all agree with that?
Yes.
Addison, can you tell me how you got that? Where that came from?
Well, to find FA of x, I did 40 times the cosine of 30 degrees, which is square root of 3 over 2 times 40, which is 20 square root of 3. And 20 square root of 3 is 34.6. So then you just use algebraic manipulation to find f of f.
Is that okay?
Mm-hmm.
Excellent. Somebody else want to tell me what you got for Fn for the normal force? Normal force, what'd you get?
78.1 newtons.
78.1. Do you guys agree with that? Yes, no, maybe, I'm not sure.
Yeah.
No.
Some people say yes, some people say no. Let's go through it. So what's FG?
Force of gravity.
Force of gravity, the value is
Negative.
negative 98.1. So I'm just going to kind of do this. I'm going to plug it in here. Negative 98.1. What's FAY? 20?
20 newtons.
And is that one positive or negative? That one's positive. Does that make sense? And then we've got the FN. So if we're going to figure out FN, it's going to be 98 minus 20. Does that make sense to everybody? So it should be less than the normal force would have been otherwise. So 98.1 minus 20. What did that get us?
78.9.
Is that okay with everybody now? Yeah? Yeah. You have to be really, really careful with the positives and negatives. If you don't take that into account, like if you forgot to make this negative, or if you made that negative, then you're going to get the wrong answer. You see what I'm saying? So you really have to pay attention to those. Other than that, how are we doing on this one? All right? Okay. Cool. Okay, hold on. I have to see what's next. I need to remember. Oh, yeah. Okay. So this one, I'm going to have you erase your whiteboards. This is kind of a conceptual question about friction. So grab that whiteboard behind you, Casey. I'm going to have you guys use that. Yeah.
With the box is moving.
Yes. It is moving.
Yeah. So if the force of friction was equal to the force that's pulling it this way,
Yes.
why is it still moving?
It's not accelerating.
It doesn't have any reason not to be.
It's not accelerating.
Yeah, it's not speeding up.
But it's also
It's just moving at a constant speed. So here, let me take my frog on a walk for a second. So,
it's so cute.
I know, right? It's a good frog.
I haven't seen happy frogs.
Yeah. Okay, so here's my frog, right? So right now, what's the net force acting on it?
0.
0. Is he accelerating?
No.
No. As I start to pull him, he's going to accelerate. But again, we don't care about that yet. That's next week. Okay? But now if I start moving, so I'm walking at a constant pace, right? Constant pace. So that means he's walking at a constant speed. Okay? So what's the net force on him if he's walking at a constant speed?
0.
0. Okay, I'm gonna turn around, because otherwise I'll leave you on, like we said. So as I'm doing this, he has a force pulling this way, right? Part of my applied force is going this way. There's also friction. Is that okay? And so he's moving at a constant speed. His net force is 0, even though he is moving. Is that okay? Does that answer your question? Did that confuse you more?
No, it's okay. You move on.
Okay, here, let me see if I can. I'm trying to think of how to answer the question I think you're asking, but I'm not sure what exactly that question
I think
is.
it's just background knowledge. Move on. I'll figure it out.
Are you sure?
Yeah, I'll figure it
Keep asking, okay? If you're still stuck, because this is like one of the. It is kind of a big deal. So I don't want it to just like fester and get lost. Fair? Okay. All right. Here's the situation. I'll do a demo of this one too, but not for long because it makes me tired. I have a book. Yes? I can draw a free body diagram of the book. We've done that except it was a frog, right? I can also hold the book like this. Yes? Okay. I want you to draw a free body diagram of this situation. That's what this question basically says. So we've taken the box, I'm holding it against a wall, and preventing it from slipping by pressing horizontally.
You could hold the frog.
No, I'm tough. I'm just not going to do it for a long time. So get this in your head. Everybody sees it, yeah? Look at me, I'm holding the book. Okay, I'm done because my arm gets tired. I would like you to work with your partners. I want you to draw it on the whiteboard. You can draw it on your paper too if you want, but this one's more just like a thinker one. You need to have at least 2 people, maybe 3 people write on that whiteboard. Share the fun. Share the fun, share the marker.
That's multiple, right?
You're right there.
Yeah, nothing's pulling it up.
Close enough.
You know what I'm saying? Yeah.
I don't think there's not a natural force, but there is
What did you just say? Did you say a bad word? Normal. There you go.
They're children.
That would be friction, not gravity.
No, it's not. But this is gravity. There's something that's making sure it doesn't fall.
No, but I'm just being short there because there's nothing underneath it that's holding it up.
And when you label your free body diagram, do it in the fancy way, the official way. Force a vet on the, right? Label them. Force of the is.
I see where you're going.
Imagine, alright.
I did it like that. She is holding it.
Imagine if she was holding it down here. She's still holding against the wall, but she's holding it up. This is that she's holding it here. She's doing a force.
Yeah.
She doesn't fall down. Is everyone okay with this?
Just write it. I still
I would think it would be forced to grab.
Okay. It's okay,
Friction,
no problem.
opposite direction than gravity.
There's really no friction.
There's no
It's not
movement.
moving.
You're kind of almost putting Rachel's trying to do a shape. Do you know Rachel?
Yeah.
There is friction though, because if there wasn't friction, there would be nothing to hold it onto the wall. So it would just slide down. Just because you put pressure.
I didn't actually look carefully.
If you put pressure onto a slippery surface, it'll still slide.
Yes, you are wrong. It's not the reaction you're supposed to have.
What? Why not? Everyone's eating work.
Oh, okay. You get more opportunities to do it right. You're welcome. I don't know.
I think that would be.
What is this?
Because if you put the book on a slippery surface, it would still slide down.
Yes, correct.
You don't think?
Yes. Tastiness, friends. Come on.
Oh.
It's not
What, did you custom build it? What kind?
She's not pulling.
I use the MSI.
I was like, I see. Oh, I know what I should. Yeah.
That's fine. That's fine. Let us.
The refresh.
Because this.
No.
Oh, wait, the walls over here.
Also, it doesn't matter how you look at it.
So I got paint on.
No, it doesn't. Because she can hold it against the wall like that, and it would be. But actually, no, that was like, because I didn't. The way she said it wouldn't make you think that, but if you read the question, they're suggesting that. Yeah, friction is keeping up. So let me see it back.
Hey.
Not fancy.
Is it fancier? Surface on the glass. On the glass.
Is it a desktop?
Sweet.
She's like me messaging.
You should get cat on it.
Another force.
So,
You should.
why is this why do I even put this on here? Why is this an interesting question that's maybe a little different and counterintuitive?
It's not.
Because it's not.
Because it's
It's the thing.
not.
What'd you say, Ray? The normal force isn't always opposite gravity, right?
Yeah.
In this case, the normal force and gravity are what?
Perpendicular.
Perpendicular one another. That's weird. Okay? But it still works. It still holds us up. Not us, but the book. Or us in the case of what? In which case does this actually hold us up, this principle of friction holding us up? Everybody's favorite ride from Adventureland
So
they
is
just
that
got rid of?
Oh my gosh.
I did. It's gone. Because it's old. It was like really bad. But anyway, it's gone now, so I hope you had time to ride it. Friction is actually what holds you up in that ride.
My walls are scratchy. The guy passed out on me. He was like, after the ride stopped, he was like,
That's awkward.
yeah, I know.
What do you do when that happens? I don't know. All right. Let's talk. Stay with me here, friends. We only have about 12 minutes left, and we have a couple more problems to do still, right? Because we're only here. Oh, man. Okay. So let's do this. We need to define force of friction a little bit more. So, unlike the normal force of friction does actually have a way to calculate it. That's fun. Okay? So we can develop an equation for the force of friction. F sub F is equal to something. What do you think the force of friction might be dependent on? What do you think it might be dependent on? The what?
The applied force? Question mark?
I like it when people punctuate their statements. It's funny. The applied force question mark. So here's my question. So if I pull really hard, is that going to change the force of friction acting?
No.
Never mind. That's why they're question mark.
That's okay. Here's the thing that you all have to remember, right? It's okay to be wrong in here, right? Because we're learning. If you all knew all this stuff, then why in the world would you even be here? Right? Like, get out and go take a different class. It's harder, right? Okay, so maybe not the applied force. What might it be?
Mass.
The mass of the object? The bigger the object, the more friction? It's a good guess.
Surface area.
Surface area, also a good guess, right? Like the bigger the box, maybe, right? So the more the mass, yes, both good guesses. The answer to both of them is actually not quite. But the answer is actually related to both of them, okay? In different ways.
Does that have something to do with like the gravity?
Yes, kind of.
Okay.
So we're going to do a lab with this. Not next week because we only have one day next week, after, but the time after. Let me tell you right now what it is. Part of it has to do with the normal force that's acting. So that's why I say it's kind of related to the gravity or the mass, and it's kind of related to, somebody said something like the force of gravity, right? It's kind of related to those things in that the normal force is often related to those things, but not always, right? Like in the book example, it wasn't completely. Okay, so kind of not. There's something else that helps to determine friction. Let me give you an example here. What if I pull the frog along this floor, and then instead of having tile out in the hallway, what if it was carpeted?
That would change.
Do you think that would change the friction?
Yes.
And if I change the frog?
Yeah, well, depends on.
Is he
Yeah.
changed? No. It's the same frog, same cute little frog. He goes on his walk and he goes out into the hallway and now it's carpeted. What has changed?
Surface.
The surface. The relationship between the two surfaces, in fact. Okay? And that thing is marked with the letter mu. Okay? Mu. So it's a Greek letter. It's up there in the middle of the Greek alphabet. Okay? It is spelled with Roman letters mu. And mu is the coefficient of friction. The relationship between two surfaces. So how sticky or slippery two surfaces are relative to one another.
So is that
Okay.
kind of like the marching from one median into like another one?
Kind of. It's not exactly the same, but it's the same kind of idea. Yeah. And mu is actually calculated experimentally. It is the force of friction. We can measure the force of friction, how hard the friction is pulling back, divided by the normal force. The reason I write it this way, I mean, these two are pretty much equivalent statements, aren't they? Okay? The reason I write it this way is because then you can look and see what the units for mu are. Force of friction has units of? It's a force, so it's a? Come on, friends. It's a Newton, right? It has been the whole time, it always will be. The force normal is measured in? Newtons.
So mu has a
Newton divided by Newton is a?
non-unit.
Nothing. Okay? Mu is a unitless quantity. Okay? It's a ratio. It's a ratio. It's going to be somewhere on the order of, it's usually less than 1. Okay? The slipperier the two surfaces are, the lower the coefficient of friction is. The stickier the two surfaces are, the higher. Okay? Life is okay? Now, one more little piece of information. Have you ever tried to push a box with your little brother in it or something? Like when you're pushing on a box and it's at rest, you have to push pretty hard to get it to move. Do you know what I'm saying? But eventually, it starts to move, and then it's easier. Have you had this experience before?
Yes.
Sometimes you can do it with something with wheels on it, but usually it's easier if it's something that's actually sliding. Okay? So when it's still, it's really, really hard to move, and that is what we call static friction. Static means stationary, still not moving. Once it starts moving, we have what we call kinetic friction. Okay? Kinetic friction is friction when we are moving. Kinetic friction is pretty easy to calculate. FF is equal to mu, I'm going to say mu sub k times Fn. And the reason I say mu sub k is because the coefficient of friction is different once you get it moving. That's why it's easier to push this thing once it's moving. Okay? The coefficient of, static friction in general is a little bit different. Let me tell you what this equation looks like. It's a little bit different. FF is, here's the difference. Whoa, don't open PowerPoint. I want to do this. Thank you. Less than or equal to. What? What? Less than or equal to? That's crazy. It's not really crazy. Let me give you an example. Right now, how much applied force is being applied to this table?
By you or none?
By me.
None.
None, right? So how much frictional force is there?
0.
0. If I was going to draw a free body diagram of this table, assuming there's not stuff on it, it would just be the earth pulling down and the floor pushing up, right? I'm going to apply force of a newton. There we go. I'm applying force of a newton. Is it moving?
No.
So is it accelerating?
No.
So what's the net force? 0. So I'm applying a force of 1 newton, so that means the force of friction pushing back that way has to be how big? 1 newton. Does that make sense? I'm going to push with 2 newtons of force. How big is the force of friction?
2 newtons.
2 newtons. I'm going to push with 5 newtons of force.
5 newtons.
5 newtons. 17, I can keep pushing, and the force of friction is going to keep going up. Does this make sense? Until, and these tables are really heavy, so I'm not actually going to do it, but until it started to move, and then it would be easier to move. Okay? So the coefficient of static friction is greater than the coefficient of kinetic friction, but the force of friction for static friction is not always equal to this statement. Okay? We okay? Because now I'm going to throw a problem at you that uses this, so I want to make sure that's okay.
Okay.
Are you ready?
Yes.
Here it comes. It's got, nope, not that one. This one. It's got E parts. Mystery box again. Rests on a horizontal floor. The coefficient of static friction is 0.4, and the coefficient of kinetic friction is 0.3. It says, determine the force of friction acting on the box if a horizontal external applied force is exerted on it. Go. I want you to think about this. I'm not going to tell you how to do this one. I want you to think about it. It might help to draw a free body diagram. What's up, Michael?
You said the static mu was always less than.
I meant to say greater. If I said less, I was speaking incorrectly. I apologize. I meant to say greater. If I said less, then I'm sorry. Retract that statement if I said that. Static is always greater. But maybe this is where the miscommunication happened. The equation for static friction is less than or equal to mu Fn. Maybe I mixed myself up because I said that. Is that okay? But mu sub s is always greater than mu sub k. That's a really ugly mu. All right. Talk to your neighbors. You've got like 3 minutes. I would draw a free body diagram if I were you. I think that will help. Once you get it, it'll be easy. And that sounds funny, but that's what I mean. Okay, I'm gonna hold on to it because it's time to go. We'll come back to this. We'll do this one right before we take our little test on, when do I see, Wednesday?
Yes.
Okay, so if we don't talk about friction on that test, but we talk about applied forces and we talk about normal and gravity, will you be okay?
Yeah.
Do you feel like that stuff's all right? Okay, fabulous. I hope you guys have a great weekend. I will see you on Wednesday. Enjoy the long weekend.
Well, probably. Do you have any ever